All right. So for question number 4, Harley, can you read that out loud for us? Do you have that?
I don't have that.
Oh, sorry. Megan, can you read it out loud for us, please?
Question 4.
Yes, please.
What is the advantage to having columns mostly made out of white matter?
What is the advantage of having columns mostly made out of white matter? So to answer that question, you have to know what do columns do and what white matter is. Okay? So columns. You have 3 columns, or 4 technically. What do they do?
Myelinated nerve fibers to make major nerve pathways, nerve tracks.
What does that mean? I don't even know what that means.
I mean, that's what I wrote down.
Okay. So what do they do? I heard some mumbling over there. Send signals. Or receives them to or from the
Brain
and rest of body, right? So if we have the definition of columns, you would say that the column, what was the word you used? Sense? Sense. Okay, so you can write sends, you can write transmits. So you send impulses. So this isn't the answer for number 4 exactly. This is kind of like building up to it. It sends impulses to and from the brain. Okay. What is white matter? What is white matter? So go ahead and take a second to discuss. All right, give you guys a hint. White matter is
Not gray matter.
Oops. White matter is kind of a type of neuron. What kind of neurons? Myelinated. It looks white because the neurons have myelin, which is fat, basically, wrapped around the neuron. So it looks white because all the fat is causing this whitish looking color. Okay? So you have a lot of myelinated neurons. Last unit we talked about if you have a lot of neurons that are nice and myelinated, covered, and well insulated, what does it allow for those neurons to do? Lexi? Send faster impulses. Sends faster impulses. So then for question number 4, it's asking why do you have these kind of neurons performing this function, basically. Okay. So for number 4, you kind of got to make a connection between, all right, well, columns are supposed to send information to and from their brain, and they're made up of white matter, which sends impulses really fast. Why would that be a good thing, or why would you want it to send it faster impulses? And when we say faster, what are we comparing white matter to? Gray matter, which is not myelinated, and therefore you would assume that it sends impulses slower. So, number 4, you kind of got to make the connection between the function and the structure here. So take a minute to kind of either revise your number 4 or add on to your number 4, or just answer your number 4 at all. I did leave out this a little bit yesterday. So on your notes, on a blank side somewhere or something, you might want to note this review here, which is there are multiple types of neurons based on their shapes. This, number 1, is the classic one that we talked about all last unit. We kind of ignored some of the other ones that are important. So for example, this shape here, number 2, is called a pseudo unipolar neuron, and this is the one that we're going to be talking about. So for example, if you had your hand, here would be the trunk of your body, which is where your spinal cord is located. So if you have a fire, you touch a fire, or you have a spider crawl onto your hand, so here is our spider, not much improved on that part, but there's your spider. It will trigger some of these neurons. So I'm going to draw one of these pseudo-unipolar neurons. Would this be a sensory or a motor neuron if you're feeling a spider? Sensory. So right about here, we have the body of the cell. In this area, and then it leads into the spinal cord where it sends out its transmitters saying there's a spider here, or there is something on the skin at this spot. Now, if we pictured another neuron, for example, you have another neuron leading from your middle finger or your ring finger, we drew another neuron here, it would kind of have the same path, and its cell body would be about right here, and it also enters through this area. So the question is, when you have a cluster of these cell bodies right here, what do we call that area? What do we call a cluster or a group or a gang of cell bodies? Ganglion. So a cluster of neuron bodies is called a ganglion. This one specifically, which ganglion is this? Dorsal root ganglion. How could you could assume that this is a dorsal root based on the fact that it's a sensory. Sensory neurons go through the backside of the spinal cord. So this is actually your dorsal root ganglion. Which means this right here, this cluster, notice how it's like literally bigger than this area. This dorsal root ganglion on this image would be this huge piece right here. This is the dorsal root ganglion, this is where all the cell bodies are. So what is this piece right here again?
Dorsal root.
Dorsal root, which means this right here would be the dorsal root, which means it leads into the spinal cord. What horn do we have here? Posterior horn. And then we have some processing via the interneurons in the actual gray matter. And then you're going to have some sort of a decision to move the arm, and that impulse is going to be sent via a efferent neuron out of the anterior horn, out of the anterior root, to the arm muscles to do something about that spider on your arm. Okay, so this is kind of a review from yesterday. Are there any questions? Yeah.
So, like, when you get the feeling that something's crawling on you when there's nothing really there, is that just the nerves, like, misfiring?
Yeah. So if you have a nerve misfire, it can depend on which nerve. If you feel like something's moving but there's nothing there, do you have afferent or efferent malfunction? Afferent. If you're sleeping in class and all of a sudden your arm randomly twitches and you wake up, afferent or efferent malfunction?
Efferent.
Efferent. Okay. And now the crazy thing is some people, all of their neurons, so when one neuron fires, since it's connected to other neurons, it will cause the neighboring neurons to accidentally misfire as well. So for example, let's say this is your brain. Okay. You have two hemispheres, of course, left and right hemisphere. I know, thank you, I tried. So if you had a neuron right here and it misfires, it will misfire and tell this one that it's connected to also fire, which will tell this one it's connected to also fire, which means this one will also fire, and this one will also fire, and all these other ones connected to each other will also fire, right? Which means since the two hemispheres are attached to each other, it will also tell everything on this half to fire as well, which will tell everything in the spinal cord to fire, which will tell all your muscles and your organs to fire, which is what we know as a seizure. You guys have heard of that before, right? Seizures. So have you ever seen someone have a seizure, or you've seen it in movies or something? What happens to them? Convulse, twitch all over the place. All their organs are actually going crazy too. And so this structure right here that connects the two halves of the brain, the one that allowed the impulse to go to the other side, this was one of your vocabulary words. Okay? This was your, oh, there's no more space to write. I'll write it down here. This was your corpus callosum for lecture 3. So the corpus callosum allows the communication between the left and the right hemisphere of the brain. All right? So in some people who have disorders such as epilepsy, which some of you might have heard of, if it gets really bad and they're having seizures every single day, what they can do, this is really radical, is since one half of the brain is causing the other half to malfunction, they can have the doctor cut the corpus callosum, just cut the cord in between. That way, this one can never communicate with this side anymore. So even if this side started firing like crazy, it couldn't tell this side to do it too. Okay? Now that means that person literally has two brains, like sitting in their skull. It is really cool. And you guys have heard the rumor like, oh, this side of the brain controls like arts and music and performance, and the other side controls like logic and reasoning. You guys have heard of that?
Yeah.
It's actually pretty true. Okay? So we're going to watch a video to see what happens to this guy who got the surgery done. Okay? And he chose to have his brain cut in half. And we're going to see what happens to him. So go ahead and pack everything up. Right. So let's recap. So here's Joe facing this direction, right? And he's looking at the computer screen at this X in the very center. He's staring very hard at it. When a word flashes to the right, which side of his brain processes it?
Left.
Left, right? So the left side will process it, and they ask him, what did you see? He says, table, or whatever he saw, so he can say it. Okay? On the next try, they flash a word to the left, which means which side of the brain is going to process it.
Right.
Right side. However, when they asked him to say what he saw, he couldn't say it, but he could draw it. Okay? So what does that mean about the area that controls speech?
It's on the left side.
It's on the left side. And there's a person who actually found that area, so it's named after him. It's called Broca's area. It's about like right here to the side, bottom-ish. And this area will control speech. Okay? But when this word was processed by his right brain, and his right brain was like, oh, the word was phone. And it was trying to tell this side of the brain there was a problem. There's a disconnect, right? The corpus callosum is cut. It couldn't tell Broca's area to say phone. So it couldn't say it. All right? So what does that mean about drawing then?
You can draw on the left.
He could draw on the right side. So maybe drawing is controlled somewhere over here. But did you see him? He was able to draw with both hands, right?
Yeah.
So which means what about drawing?
Both sides.
It's on both sides. Okay? So speech is here. Drawing is somewhere both sides. Now, the catch is, I don't know if you noticed, they said, here, draw it with your left hand. Why did he have to draw it with his left hand? The left hand, the left side of your body, is controlled by the right side of your brain. If they had said draw it with your right hand, what would happen?
You wouldn't be able to.
You wouldn't have been able to do it because this side of the brain didn't even see it, so it wouldn't have been able to say, hey, right arm, draw this. Okay, so it's pretty trippy and it's pretty crazy. And there's a lot of really cool disorders, not cool, unfortunate disorders. For example, there are people who have Broca's area like completely messed up, which means they can't speak. But the cool thing is that the center that controls singing is somewhere else. So there are some people who have this disorder called Broca's aphasia where they can't speak, but they can sing everything. So then, yeah. So if those people like train hard enough, they can actually just like normalize the tone and sound like they're talking, but in reality they're actually singing. So crazy.